All right, so let's begin. Today what we are going to see is we are going to talk about a new chapter called series, right? And so this is called series. So in particular, we are going to talk about infinite series, right? So you have learned about series in your advanced level, right? So they talk to where you were told about some series, and then you were told about how to find the limits of those series, right? And then looking at the conversion of the series just as examples or exercises, right? You were just taught how to look into something called series and then convergence and other properties of the series, right? Especially finding the sum of the series by using the recursive notation or recursive formation of the series, right? So we are going to study a little bit deep about series here, right? So in particular, we will introduce series and we will study a little bit deeper than what we have learned in A level, right? And try to have an understanding about series here. Right? So that is how this course, this part we are going to do, right? So in order to do that, let us first define what do we mean by series, right? So to define a series, we should have a sequence, right? So we should have a sequence, right? So the sequence, you know, right? So let this be a sequence, right? Let this be a sequence. So once you have the sequence, what you do is you start defining something called partial sums, right? So sequence and their properties we have already learned in chapter 2. So we are going to start with the sequence and try to develop a right? So what we are going to do is to what we are going to do is we are going to define something called partial sum, right? Right, so we are going to define something called partial sum here. Right, so how we are going to define partial sum is you take the first component as S1, right? And so you take S1 is equal to U1. And then what you do is 2 is equal to S1 plus U1, right? So you take S1 as S1 plus U1, right? And then S3. S3 is obviously, sorry, U2, S1 plus U2. And then S3 is S2 plus U3.
The board is not
in this fashion, right? So in this fashion, we try to develop something called partial sum, right? So once we develop this partial sum, right? Right. So once we develop this partial sum, this is turned out to be a series, right? Okay, so right? So when we try to define the partial sums, so basically we are defining a new sequence, right? S1 is an element, S2 is an element, S3 is an element. So we start finding new elements, right? So then in that way we are making a new sequence, right? So once we see the partial sum as a sequence, and then if we can prove that the sequence, which is a set of whose components are partial sums, right? Then we can say that the series summation of un, right? If un is a sequence, then summation of un's, right, which is basically the partial sum, right? So that converges, right? So that is how we define the convergence and convergence of a series, right? So I will bring a new marker and come back. Okay, so we have defined the partial sum, right? Sequence, right? And then based on the convergence of the partial sum, we talk about the convergence of the series, right? Series, which is summation of un, right? So here you know that what we mean by the notation, right? So right, once the sequence Sn is converging, right? So you have summation of Sn, right? So you have limit of Sn, right, that exists, and that is a number, a value, right? So in that case, we call that as the sum of the series. Right? So this is called the sum of the series. Right. So now you know the sequence and how to find the limits of the sequence. So once you know how to find the limits of the sequence, then it is easy to find the sum of the series, right? So it is not a big deal anymore, right? Because by using the knowledge you have in chapter 2, you can always find the sum of the series, right? By just defining the partial sum and taking the limit of the partial sum. That is all what you need to do, right? So now again, in sequences, we see certain results, right, involving sequences. Especially we see that when xn and yn are two sequences, both are converging, right? then we see that xn plus yn converges to the limit of xn plus yn, right? And then xn times yn, we have a we know that it converges to L times m. Xn minus ym converges to L minus m, right? So all those results we have studied, right? So by using the same idea, we can define similar kind of results for series as well, right? So here is one of the okay, so here is one of the results which we are going to prove, right? So I'm going to write it as propositions. Right, first thing is sum of the series, right? And so let summation of un and summation of vn be two converging series, right? Then the first result is summation of un plus vn converges. In addition to that, right, the limit right, so the limit is summation of un plus summation of vn, right? So limit of the sum of two series is basically sum of the limit of the series, right? So that's one result. And second one is when you multiply by a constant number, right? So summation of lambda times un is the same as lambda times summation of un. Right? So we have two results. So by using those two results, we shall, right? So we shall prove the convergence of, we shall prove these two results by using the partial sum property, right? So the property we studied in sequences, because partial sum is a sequence. So by using partial sum and using the results we studied in sequences, we can always prove the results in series. So here, this is what we are going to do first. Okay, so first we put partial sum, right? First part, right? So we define two partial sums. Partial sum for UK, right? The series summation of U, and then partial sum for the summation of V, right? So let us name Sn be the partial sum of the series Un, right, for finite n, k running from 1 to n, and Tn be the partial sum for the series summation of Vk, right, for 1 to n. Right? So then we can define, we can see this, right? the partial sum of un plus vn right? So this is just a property of real numbers, right? We see that in the first chapter, right? So when you add two numbers, right, you can change the order and add, it is still the same addition, right? So a plus b plus c, you can add a plus b and then c, or you can add a and before that you add b and c and then you add a, right? So you can do, and you can always say a plus b is same as b plus a, right? So by using all these properties, you can easily see that summation of uk plus vk is same as summation of uk plus summation of vk, right? So right, so in that case, you can easily see that Rn is basically equal to Sn plus Tn, right? So in terms of partial sum, we have a relationship between Rn, which is the partial sum of uk plus vk, and Sn, which is the partial sum of uk, and vk, which is the Tn, which is the partial sum of vk. So now we can apply, because now it becomes sequence. From series, you ended up with sequence. Sn is a sequence, Tn is a sequence, Rn is a sequence, right? So that is why you always get partial sum whenever you are dealing with series, right? So whenever you are dealing with series, you have series, which is a summation of numbers, right? But when you take it in, when you convert it into partial sums, then you ended up with a sequence, right? A sequence of numbers, basically a sequence of partial sums. So when you have sequence, you can always go back to chapter 2 results and apply those results here. So now, because these are sequences, right? So you know that, right? Right, because you know these two are converging series, right? Summation of u and summation of d are converging series. So clearly Sn and Tn are convergent sequences, right? Are convergent sequences, right? So you know that. If they are converging sequences, then you know right? Because if they are converging sequences, then you know, right? Limit of Rn is basically limit of Sn plus Tn, that is because of this relationship, right? But limit of Sn plus Tn, by what we learn in chapter 2, is equal to limit of Sn, n goes to infinity, plus limit of Tn, right? N goes to infinity. This results is because of the results we studied in sequences in chapter 2, right? So this equality has to deal with what we learn in chapter 2, not in this chapter, right? So that is why chapter 2 is important, because we incorporate chapter 2 here, and we will incorporate this chapter 2 in the maths we are going to study in the next semester as well, right? So in the second semester courses also, this what you learn in chapter 2 will come again and again. So chapter 2 is very important for a longer period of time. So now this is quite clear, right? So this is, if this is true, then clearly you know this is summation of un, right? N goes to 1 to infinity is basically plus dn, right, is basically equal to, this is summation of un plus the other one is summation of v. Right? So that is how you prove that when you add two series, right, the sum of the addition is equal to addition of the sums, right? So that is the first results we have here in the series. The second one is you have to take summation of lambda u. Okay, so for second one, you will see lambda u. So let me name another thing, right? So I can use Sn again, right? So Sn be summation of k is equal to 1 to n lambda times uk. Right? So let this be my partial sum for the second results, right? Because my second sequence is summation of lambda times un, right? So in this partial sum, you will have a lambda. So let me name Sn be my partial sum here. So this is clear for you that this you can always take lambda out and write it as k running from 1 to n uk. Right? So sorry, it's because I use Sn here, I have to use a new notation, right? STR UV. Okay, let me say WN. Okay, so let me use a new notation. WN is the partial sum of lambda UK, right? But lambda UK, you can take the lambda out, so lambda times summation of UK. But you have summation of UK as Sn, right, here. So you can say this is lambda times Sn. So now you have two sequences. Wn is a sequence and lambda times Sn is a sequence, right? So clearly again, Sn is a convergent sequence because it says that summation of UK converges. So limit of Wn n goes to infinity is same as limit of n goes to infinity lambda times Sn. Right? So again, this is as results we studied in chapter 2, right? Lambda times Sn, limit of lambda times Sn is same as lambda times limit of Sn, right? So that is because of the sequence property, right? So this clearly says this is the infinite sum, right? Summation of lambda un is basically equal to lambda of summation of, right? So clearly this is true, right? And before that, you know, because this limit is finite, right? The summation of lambda un converges at the same time. This one is okay. So now you know that if, right, the limit of the sequence is a finite number, right, then we call that the series. If the limit of the partial sum is a finite number, then we call it as a convergent series, right? So if it is not a finite number, then obviously the series will not converge, right? So in that case, we have to say the series is divergent. So let me redefine both of them. Okay, so let me write this as a remark here. Right, so if the sequence has a limit, right? Sequence means the sequence of partial sums, right? So you know the notation, so I don't need to rewrite it again, right? So if the sequence of partial sums is a converging sequence, and if the limit of that is a finite limit, right? So then we call the series which gives you the partial sum as a convergent series. So that is what we learned already. So what will happen when the limit of the sequence is infinite, that is plus infinity or minus infinity, right? So in that case, we call that series as a divergent series, right? So the convergent opposite is divergent. So if the limit of the partial sums is infinity, right, both plus infinity and minus infinity, then we say that the sequence is divergent, right? So now we will see an example of a divergent sequence as well. An example, right? So let us define a series like this. Right, the nth term in the series is a minus a plus n minus 1 times d, right? For some real numbers a comma d belongs to real numbers and fixed, right? For some fixed numbers a, right, you take un as this. So clearly you can see the numbers, right? So u1 is a, u2 is a plus d, u3 is a plus 2d, right? So you can see that, right? So this is how the series is going to, or some terms of the series is going to look like, right? So now the question is, right? So what this series will do, whether it will converge or whether it will diverge, right? So that is something we have to look for, right? So this is what, whether convergent or divergent is something we are going to look for, right? So obviously, if you want to look for convergent or divergent, then the first thing you have to do is you have to go for the partial sum of the series, right? So let us start finding the partial sum. Okay, so we are going to find the partial sum here. And so you obviously know the notation of partial sum, that is Sn. So I can say k running from 1 to n uk, right? So that is clearly k running from 1 to n, right? A plus k minus 1 times d, right? This is the term uk, right? So when you write this, your uk, if un is a plus n minus 1 times d, uk is a plus k minus 1 times d. So clearly that should be your k term, and so that is the partial sum, right? So now what we do is we separate the summations, right? So there are three terms here, so I'm going to separate it. So this is k running from 1 to n, right? A plus summation of k running from 1 to n. I can take the d out, right? And then k minus k running from 1 to n d, right? And so that is, or I can put d inside first and then show you how to do it. So dk. So you separate the terms, right, by using the property, right? So now what you are going to do is you are going to take the sum here, right? Summation of a over k running from 1 to n. So you are adding a n times, right? A plus a plus a plus a. So that is clearly n times a, right? Plus here you have a d, right? And you have a summation of k, right? So you have a summation of k. So that is, right? So you can find summation of k, that is 1 plus 2 plus all the way up to n, right? So you know this sum, right? From A level or O level, you know this, right? So this is n times n minus 1 over 2, right? So that is something you know, right? So that's clear. And then this one is minus, sorry, n times n plus 1, right? Yeah, n plus 1 over 2. And so if you, this summation is n times n plus 1 over 2. Right? 1 plus 2 plus 3 plus so up to n is n times n plus 1 over 2. Right? So this is summation of d, so n times d. So now you can combine all of them. Right? So you take n over 2 out. Right? So when you take it out, you get 2a, right? Plus, and you take a d out. So you already take n out, this out. So when you take n out, it is n plus 1 minus 2n. So n plus 1 minus 2, so n minus 1. Right, so this will be your partial sum here. Right, so this is just manipulation. So you know that you can take the partial sum. Right? So now what to do, once you simplify the partial sum, you can take the limit. Right, so now you have partial sum in a simplified form. So now you can take the limit. Right? Limit of n goes to infinity Sn is basically limit of n goes to infinity of this term. So that is n over 2 times 2a plus d times n minus 1. So this whole thing is multiplied by n over 2, right? And you are taking n goes to infinity. So clearly, right, when you are taking n goes to infinity, this term, irrespective of what this one is, this n over 2 will always dominate and it will push everything towards infinity, right? Depending on whether D is positive or not, right? So you can see that right? If this term is minus, right? This whole thing will be minus, right? And this term is minus, then when n gets larger, this term will become minus and Sn goes to minus infinity, right? Right? So you can see that depending on the sign of the D, right? So depending on the sign of the D, right? You can see that if D is negative, then when n gets larger, this one become a big minus number and A is fixed. So 2A is a fixed number, but this one gets large, 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 and eventually it will be a big minus number than 2A. So the whole thing inside the bracket will be minus. So when n goes to infinity, this goes to minus number and this goes to infinity. So eventually it all goes to minus infinity. And if D is positive, then when n gets larger, this gets larger, positive, positive, positive. So all of them are positive. N goes to positive infinity. So eventually everything goes to positive infinity. So in any case, right, the limit of the sequence is infinite, right? It is either plus infinity or minus infinity, irrespective of what you have for A and D, right? So clearly you know that it is a diverging sequence, right? Right? So because the limit of the sequence is infinite, right? The series is a divergent series. Right? So this is one example of divergent series. So next is an example of a series which is convergent and divergent depending on what you choose for the numbers. Right? So next example, I'll just give an example and give you a hint of how to do it and leave the work as a homework. And so this is the most famous series you know, right? It is called geometric series, right? So that is the clear thing. Right? So this is a series called geometric series, right? So in this series, you know, it is basically a times r to the power n minus 1. Right? So it is a geometric series. A times r to the power n minus 1. So you clearly know the series, right? So you know U1 is A, U2 is AR, U3 is AR squared. So eventually UK is A to the power R K minus 1, right? So that's how the series will look like. So now the question is again whether this will be a convergent series or divergent series, right? So that is something you have to look for, right? So first you have to find Sn. Okay, so first you have to find Sn, right? Summation of uk, k running from 1 to n, right? So this Sn is going to take two cases, right? Itself is going to take two cases. So you try to verify that, right? So it is going to be n times a if r is equal to 1, right? Because when r is equal to 1, 1 to the power n minus 1 is always 1. So the series is u. So when you sum it n times, it is going to be n times a, right? So that is for a special case, r is equal to 1. They say r is any real number, right? So as long as r is 1, this term is always a. So when you sum it n times, it is going to be n times a. So that's clear. Now the other case is if r is not equal to 1 case, right? So when r is not equal to 1, you probably know the sum, but you can always find it, right? Right, so if r not equal to 1, we have Sn is equal to, right, a times 1 minus r to the power n over 1 minus r, right? So you can take the sum, right? So a plus ar squared plus ar cubed, and so all the way up to ar n minus 1, right? So you can sum that series and you can always find it, right? So that is not a big thing. You must have done it in A level, right? So now the problem is you have to look for the convergence. So already your partial sum is of two cases, right? One is r is equal to 1 case, and the other one is r is not equal to 1 case. So first let us take r is equal to 1 case, right? Right, so if r is equal to 1 case, right? So you know that it is clear, right? So right, so when n is r is equal to 1 case is quite easy, right? So when you take limit of Sn, it is basically limit of an, right? N goes to infinity. So if a is positive, right? If a is positive, this goes to plus infinity, right? So if a is positive, right? If a is negative, it goes to minus infinity if a is negative, right? So a is equal to 0 case gives you nothing, right? You cannot take a is equal to 0 case, right? There is nothing to work if you have a is equal to 0, because if you have a is equal to 0, all the terms in the series is 0. So it is summation is 0. So you don't need to worry about a is equal to 0 case, right? So that is why I don't even bother about a is equal to 0 here. So a is positive infinity, a is negative infinity. So that is quite clear, right? So this is divergent. So in this case, right, summation of un diverges because infinity. Right. Now the other case is you can show that the sequence converges, right? So what we are going to do is we are going to show that the sequence converges. That is the second case if r not equal to 1, right? So you can try to see what will happen for this series, and you can always work it out and try to simplify and see the limit, right? So basically you can prove this, right? Right, so if absolute value of r is less than 1, right, so yeah, then you can easily prove that the sequence converges, right? So that's not a big deal, right? So you can, right, so this is an additional exercise, right? After proving this part, right, from this you can also prove that the sequence Sn is convergent even if and only if absolute value of r is less than 1, right? So I leave it as an exercise, and if you have time later on we can do it, right? So now what we are going to do is in the next class, right, so we are going to see more results regarding the convergence of the series, right? So obviously, you know, we are going to use, we have several criteria for convergence in the sequences, right? So we obviously start with the limit of the sequence, and then we say monotone convergence theorem, boundedness, and then we have Cauchy condition, subsequences, lots of things we studied in sequences. So here, today what we see is always you can convert a series into a sequence by taking the partial sum, right? And then convergence of the series is directly related with the convergence of the partial sum sequence. So, to see the convergence of those sequences, we can always try to verify all the criteria we studied in chapter 2. So in Monday class, that is what we are going to do. We are going to see the Cauchy criteria and other convergent criteria and try to implement how, try to see how we can implement all of them inside this series. Right? So we will stop here and then continue on Monday.